Hey everyone, it's Fig back again. This week we're going to explore solving problems with lenses using the equations. Just like we did with mirrors, we started by looking at where images formed by making ray diagrams. And then we saw that there was another way by using the mirror equations to solve a mirror problem and predict where an image is going to be. Same thing with lenses. Last week we looked at the property of lenses, how to draw the ray diagrams, and saw that there's a lot of similarities between lenses and mirrors. So we're going to see that again using the equation approach. But first, let's review some properties of lenses. All right, so we have the two basic types of thin lenses here. I have a convex lens on the top and a concave lens on the bottom here. So reminding ourselves of some of the things about a convex lens. First, a convex lens is thicker in the middle. Any lens that's thicker in the middle than at the outer edges will behave like a convex lens. A convex lens causes parallel rays to converge. That is, if I have two rays of light parallel to the principal axis, as they come through the lens, they will bend towards the principal axis and cross at the focal point. This is why a convex lens is often referred to as a converging lens. Depending on where you place the object, we saw that you could get a real image from a convex lens, you could get a virtual image, or if you put an object exactly on the focal point, then the rays became parallel and we had no image. So if you remember back when we talked about spherical mirrors, in a lot of ways a convex lens behaves like a concave mirror. A concave mirror also could create a real, a virtual, or no image if the object was placed on the focal point of the mirror. All right, well, what about a concave lens? Well, concave lenses are thinner in the middle. Now remember, this is generally a round piece of glass. Here's an example of a very thick convex lens. So we're dealing with a round piece of glass, and so this represents thinner at the center of the glass, thicker at the edges. So any lens that is thinner in the middle and thicker at the edges will behave like a concave lens. Now, a concave lens causes rays parallel to the principal axis to diverge, that is, bend away from the principal axis. So here are two parallel rays. As they pass through the lens, they will be bent outwards, away from the principal axis. Now, they will bend outwards as if they were coming from the focal point on the same side that the light started from. So notice with a convex lens, the light is bent on the focal point on the opposite side of the lens from where the light started, where a concave lens, the light bends outwards from the focal point on the same side as the initial rays. And a concave lens will only make a virtual image, cannot make a real image. And if you remember, this is very similar to how a convex mirror worked. So a concave mirror works like a convex lens, and a convex mirror works like a concave lens. So that can be a little confusing. So what you really want to think about is whether or not the object can bend the light in, that is a converging object, or spreads the light out, a diverging object. Okay. So what are the equations to deal with this? So, oh, wait a minute, this is the wrong slide, right? So these are the mirror equations. So remember the mirror equations? We had magnification equals height of the image over the height of the object, equal to minus Q over P, where Q is distance to the image and P was distance to the object. And then we had that the mirror equation was 1 over the focal point equals 1 over the distance to the object plus 1 over the distance to the image. So there should be similar equations for the lens. So these are the mirror equations. So let's see if we can come up with equations that'll work for lenses. So let me take a minute here and Yeah, there we go. Okay, and we are done. There you go. There are the lens equations. In fact, you might notice they're pretty much the same equations. They are the same equations. Now, if you remember, if you actually watched the derivation of these equations when we did spherical mirrors, these equations come from basically setting up similar triangles with the light rays coming from the object and making the image. We could do the same thing with the lenses, but those of you who made it through that derivation, it's not the most exciting thing, similar triangles. So I'll leave it as an exercise for you to do if you wish. But it ends up you get the same equations. Now, there are differences, though. The differences is those sign conventions. Remember that when we were using the mirror equations, we had to be very careful of what of these variables we made positive or negative. Same thing when we're using them for a lens. These equations will only work if you use the correct signs for the variables. That is for the HI, HO, F, P, and Q. They all must have the correct signs. Now, before we go on, I do want to remind you, some other books or some videos you'll see online, P and Q are the traditional variables we use. Remember, P stands for distance to the object. Q, which looks like a reflection of P, is the distance to the image. Some people will just call this DO for distance to object and Q to be DI, distance to image. So, whatever works for you, but I'm going to stick with these variables because it's what's in the text. All right, so let's remind ourselves what these sign conventions are in order to use these equations. All right, so for these variables, there are basically three conventions that you have to remember. First is for the distance to the object and the distance to the image, P and Q. In this case, that distance would be measured from the center line of the lens. If the object is real, then the P is positive. Our objects are always real because we're only dealing with a single lens. If you're dealing with a single lens or a single mirror, your object is real. The image could be real or virtual. If the image distance is real, then Q should be a positive number. If the image is virtual, then Q should be a negative number. Now remember, a strong indication of whether you have a real image is a real image from a single lens or mirror will always be inverted. So if your image is upside down, you're dealing with a real image. The definition of a real image is one that you can project. That is, you can shine it on a piece of paper. Virtual images you can't project because the light's not converging in the right at one location. So, but if you're dealing with a real image, your Q is positive. If you're dealing with a virtual image, your Q has to be negative. The focal point. Well, here's where a little bit tricky, because when we looked in the mirror, we could see if the focal point was on the same side as the object or on the side opposite of the object. You don't want to do it that way with lenses. A focal point is positive for a lens when the lens is able to converge light to the focal point. That is, when you're dealing with a convex lens. A convex lens is often referred to as a converging lens. A convex lens has a positive focal point. A concave lens spreads the light away from the principal axis. It can make the rays diverge. A concave lens is often called a diverging lens, and the focal point in that case is always a negative. So if you're solving a problem and you know your lens should be convex, when you're done, you should get a focal point that's positive. If you get a negative focal point, it means you probably did something wrong mathematically, and you should go and fix it. The final rule is for the heights. The height of the object and image. If the height of the object or in the image are upright, that is not upside down, then they are positive. When they're upside down, we make the heights negative. Now, almost all our objects we just consider upright, so we're really talking about an image here. And again, because we're only dealing with a single lens, real images will tend to have heights that are positive, and real images will have heights that are negative because they're upside down. And then virtual images will tend to have heights that are positive because they're upside right. So again, if you know you're dealing with a virtual image and you solve for the height and it doesn't have the right sign, you know you probably did a math mistake. So let's explore this, and then let's just do some examples. So first, the ray diagrams are always really useful when you're trying to solve the problems mathematically. Here are our basic 3 situations we have with lenses. Okay, so I have 2 examples of what happens with a convex lens on top, and 1 example with what happens with a concave lens. So let's just go through what the signs of these variables are. All right, so first, on this first picture here, the object here is a real object, and so the distance from the lens to that object should be positive. So P would be a positive number. Well, the focal point, this is a convex lens. All convex lenses are converging lenses, and so their focal point must also be positive. The object is upright, so the height of the object must be positive. So if I'm doing a math problem, I know that these 3 things should work out to be positive numbers. Now, in this case, I am closer to the lens than the focal point. The object is closer to the lens than the focal point. Notice that although this is a converging lens, in this case, the light does not converge. The light is diverging, creating a virtual image. So, because I'm making a virtual image, this distance must be negative. Now remember, this is the big difference between mirrors and lenses. If this was a mirror, the virtual image would occur on the opposite side. But because it's a lens, the virtual image occurs on the same side as the object. This is why you can't look at where the object image is and remember it left and right. You have to think about whether it's a virtual image or a real image. So since this is a virtual image, Q needs to be a negative number, but the image is upright. All virtual images will be upright, and so the height of the image is also a positive number. All right. So whenever a convex lens makes a virtual image, this should be the way the variables work out. Now, if I place my object further away from the lens than the focal point, it's going to create a real image, an image that I can shine onto a piece of paper. But the fact that my object hasn't changed, it's still a real object, it's still upright, this is still a convex lens, so the focal point is still positive. So these first 3 variables should have the same sign as before. But my image now is a real image. I can shine it on a piece of paper. So this distance should work out to be a positive number. And the real image is inverted, so the height of the image is negative. And there you go. For a concave lens, remember, is a one-trick pony. Can only make a virtual image. So the object, though, is still real. Right? That's something I've stuck in front of the lens and I'm looking at it. So for the object, the P is, of course, positive. And the object is upright. So the height of the... Oops, sorry, I skipped a variable. Because this is a concave lens, this is a diverging lens. This will take the parallel rays and make them diverge, and so the focal point must be negative. So if you're doing a problem, you know you have a concave lens, you have to make the focal point negative. If you're solving a problem and it's a concave lens and you're solving for F, the math should tell you it's negative. So that's the strong indication. Now, the height of the object is still upright, so that's positive. This is making a virtual image, so Q should be negative, and the image is upright, so the height of the image should be positive. So really, this comes down to the 2 numbers that are tricky to keep track of is what's happening to your Q, negative when it's virtual, positive when it's real, and that focal point. And the best way to understand about the focal point is convex lenses, always positive. Concave lenses, the focal point is always negative. Also, I've been saying focal point. Sometimes I say focal length. Both are appropriate. For lenses, we often talk about the focal length. Often it means the same quantity. Some people, depending on the context, will say focal point. Some people focal length. So don't be confused by that. Whenever you see the word focal, we're talking about this distance, the point where the light is focused from the lens or the mirror. All right. That's all there is to say. The nice thing about optics is, since you've already learned this when we did mirrors, it's all the same equations and all the same math when we do lenses. There's nothing really different here. The ray diagrams look a little different, but even though they follow the same 3 basic rules as we did with mirrors, the tricky bit is getting these signs right when I'm working with a problem. So let's take a look at 3 example problems. I'll work them out on the computer. And then you can do this week's assignment. Okay, let's get going.